Hello, everyone. Thank you for joining us today on our very first Twitch stream. We are excited to be here. We are hoping that this will give us the opportunity to do some new things that we haven't done before and maybe do some more sustainable projects. We are happy to have you all here for those of you who have made it. One quick thing, if you would like to ask questions in the chat, you'll need to create a Twitch username. So go ahead and do that. And then come back and follow the channel, and we'll get started. So, Chris, why don't you just welcome everybody, and then we'll get started with questions.
Okay, welcome everyone. As Matthew said, we've moved the food dish a little, so apologies to those of you who are disrupted by that, but hopefully this will in the end be as seamless and as useful and give us new opportunities. And you know, Google and YouTube don't actually have to own everything. We live in the Googleverse, but that's what we do. But Twitch has some interesting potential for us. So yes, the floor is open for your questions on astronomy.
All right, so we are starting to get it. We're going to wait a few minutes for other people to join, but there's been some very exciting news in the planetary science world, which we will have you talk about for the OsirisRex mission. But let's wait to make sure that everybody's on. So we'll take a question from email from Jan Campos or Jan Campos, who would like to know, last week a question on globular clusters sparked my curiosity. Have exoplanets ever been found there? And can you expand on why these globular clusters are found in the halo?
Right, that's an interesting question. At the moment, I don't think any exoplanet's been found in a globular cluster. People have actually tried to look using the microlensing technique, but that's a statistical method that has only turned up a few dozen exoplanets out of the thousands found. So it's a low probability way to find exoplanets. We do think that exoplanets will exist around stars in globular clusters, although these are dense stellar systems. The stars are not so closely separated that their interactions would disrupt planetary systems, except in a few cases. So stars in a globular cluster should be able to host planets and retain them. These are old stars, and that's one of the interesting things about globulars. They're the oldest stellar systems in the galaxy. The other reason we haven't found exoplanets there is that globular clusters are mostly in the halo of the galaxy, so they're distances of thousands or even tens of thousands of light years. And most exoplanets, as you probably know, have been found at smaller distances where it's easier to detect them. So we think there would be exoplanets there, and I know there are a few experiments to try and find them. In terms of what we might expect, though, these are stars that formed early in the history of the galaxy when there weren't as many heavy elements, for instance, and that would mitigate against the presence of large numbers of planets, since the planets form out of the rocky material that's left over when a star forms at the periphery of the solar nebula. And so it's possible that the incidence rate of planets in globular clusters around those old red stars is actually lower, but we simply don't know yet.
Excellent. Thank you very much. The next question is also from an email. The question is it dangerous to look at an eclipse with your naked eye? And if so, why is that?
Absolutely. A really strong advisory to never look at an eclipse directly, because even when the sun is completely eclipsed by the moon, and so it appears to be blotted out and appears to be dark, there's quite a residual amount of light that passes around the moon, the halo of the sun, the corona of the sun. That's a significant amount of light, but the real reason is that as the sun emerges from totality or goes towards totality, it's extremely dangerous. Even if you're looking at maybe 5% or a few percent of the sun's brightness, that's certainly enough to damage your retina. A full sunlight, of course, will cause blindness in a very short period of time if you just stared at the sun. So it's just too hazardous to play with looking at the sun directly, even when it's occulted by the moon for a very short period of time. So the best way to do it is indirect viewing. You have to use eclipse glasses, and you have to use sanctioned ones. During the Great American Eclipse of 2017, there were some scam eclipse glasses, and so astronomy societies had to provide links to reputable sources of these glasses, because if they're made of the wrong kind of materials, which are imperfect screening of the sunlight or have holes or blemishes, then again, you could damage your eyes with false sense of confidence in the glasses. So there are legitimate glasses. You should look at a website from Sky and Telescope or Astronomy Magazine, one of the reputable astronomy vendors. And in fact, Galileo died sunblind. He had lost his eyesight as an old man, but not so old he would have lost his eyesight for other reasons, because he was a little too careless in his observations of the sun over the years. So the best way is through glasses, or you can use indirect viewing. You can certainly cast the light from the sun through a pinhole camera, for example, and observe the transmitted image of the sun on a flat surface or a white surface. That's a totally safe way to look at the sun. And those are really the only two ways.
Kind of as a follow-up question, there's a cultural question from one of our live viewers, Pervmeng, who would like to know, is it required to watch an eclipse on an empty stomach? Apparently that's the tradition in Asian countries.
I did do an eclipse in Indonesia, the one off the coast of Borneo a few years ago, and I heard this because I was in Asia, in Southeast Asia, that is a purely Asian tradition. I don't even know what the origin of it was, and I asked people and they couldn't tell me. And I've never heard that in the West, in the United States or in Europe. It seems like you can watch an eclipse under any condition of hunger or satiation, and it doesn't really matter.
All right, thank you very much. The next question is from Jant8, who's on with us live. Having dual theories for a basic thing like light, how can we expect to have a strong base for everything made over it? So apparently they think that there's some dueling ideas about how light works, and the building on that base would mean that everything else on top of it would not be very sturdy. Can you talk about that?
Right, that's a fair concern, actually. And what you're asking about is the duality of light, where light has some attributes that are similar to those of particles, and light has other attributes that are similar to those of waves. And both statements are true. So we can give examples of situations where light is wave-like, where, for example, light exhibits interference, where it diffracts and refracts, and these are properties of waves. But light also has some properties of particles. It carries energy, it carries momentum, and those are particle-like properties. And it also acts as if it comes in small discrete packets called quanta, and that's a sort of particle-like behavior. So in the quantum theory of light, these issues are resolved because light is able to simultaneously have both of these properties. And I think the way that that's described in a way you can visualize in quantum theory is to consider light as being a light packet, a photon to be a light packet, not a hard-edged bullet, if you like, but a distribution. Imagine a waveform which tapers at either end, and so it's finite. It exists over a limited period of space, but within that space, it has wave-like properties. And that's how light could be both discrete, having a particular energy, as in the quantum theory, and having a particular localization, as in a photon, and yet have wave-like properties. So in fact, the duality of light is not a problem for the theory. It doesn't erode the foundation of the theory that light has these dual properties. The way you perceive light depends on the situation of the observation, depends on the kind of experiment you do, whether you will manifest mostly the particle-like behavior of light or the wave-like behavior of light. They're equally valid and true.
Excellent, thank you. Rentgen 101, who's on with us live, would like to know, at what time after the Big Bang would an observer have been able to communicate to one another, or not at all?
That's an interesting question, and we can wonder when the first observers in the universe exist. That's an interesting question in its own right. How soon after the Big Bang could planets form, and biology and intelligent creatures that might be considered as observers? But let's just forget about that for a moment, because that might have taken hundreds of millions of years or even 1 billion years for planets to form and life to evolve. If there had been hypothetical observers in the universe early on, when could they have communicated with each other? And the simple answer is not until quite a while after the initial expansion. At the time of the microwave radiation that we see, which is almost uniform across the sky, that's 300 or almost 400,000 years after the Big Bang. Every point in space was moving away from every other point in space at nearly 60 times the speed of light. So any hypothetical observers that amount of time, less than 500,000 years after the Big Bang, could not have communicated with each other because they were receding too quickly. In fact, observers could only communicate with each other when the expansion rate of the universe, decelerated by dark matter, had slowed to the point where the expansion rate between any 2 points was less than the speed of light. And at that point, signals could pass between distant observers. And that actually took 5 or 6 billion years. So really, for the first chunk of the universe's history, observers could not really have communicated with each other because they were being carried apart by the expansion faster than light could travel between them.
Texadactyl, who's on with us live, would like to know if you could contrast a gravity wave to a conventional electromagnetic wave.
Sure. The difference between gravitational waves or gravity waves and electromagnetic waves is quite substantial. Electromagnetic waves are fundamentally oscillating and electric magnetic fields. Those magnetic fields are coupled, and in the derivation of electromagnetic theory by James Clerk Maxwell, the electric field is oriented 90 degrees away from the magnetic field, and they both oscillate with a sinusoidal frequency. And that frequency is, of course, the distance, the number of waves that pass per second, and it's associated with a wavelength, which is the distance between peaks and troughs. And all of these waves travel at the speed of light, 300,000 kilometers per second. And they obviously travel through a vacuum and some solid materials like glass and water. So that's electromagnetic waves. Gravitational waves are a completely different phenomenon because they're not associated with electric or magnetic fields. They do not travel through a medium. They actually alter the medium of space-time itself. So in the theory of general relativity, as a prediction of general relativity, when masses change in the universe or are perturbed or a mass configuration changes or compact objects merge or collide like black holes, then ripples in space-time are sent out at the speed of light. And those ripples indeed can have wave-like properties and sinusoidal properties, so they'll have a frequency and they'll have a wavelength, but they are actual ripples in space-time itself. They're not electrical and magnetic oscillations in a medium, either a vacuum or a material medium. So a really fundamentally different type of phenomena, entirely different phenomena. And gravitational waves can only be understood in terms of general relativity.
Excellent. Thank you very much. The next question is from Sarcastrophe 143. Is the size of the Milky Way increasing as time passes?
No, the universe is expanding, and that was first shown by Edwin Hubble in almost 100 years ago, where almost all galaxies are moving away from every other galaxy. Some galaxies are exempt from that. We're moving towards Andromeda, for example, by our mutual gravity, and galaxies in dense regions of space like the Virgo cluster can be bound by gravity to one volume of space. So generally, galaxies are moving away from each other in the expanding universe, but individual galaxies are not expanding because of this cosmic expansion, because they are held together by their internal gravity. And as we've learned in the last few decades, that internal gravity is dominated by dark matter, not by the stars in the galaxies. It's long been clear that the number of stars in the Milky Way or all the other galaxies we can measure is insufficient by a factor of 5 or 6 to keep those galaxies intact. If all the matter in galaxies was the stars we see, they would indeed be expanding with the universe, but they're not. They're held together intact without changing in size because of dark matter. We don't know what the dark matter is, but we see its influence throughout the universe. We can measure the amount of it relative to normal matter, and that's what gives us confidence that galaxies, including our own, are not expanding.
The next question is from one of our live viewers, Narasha Pradhan, about the relativistic jets from a black hole. Do we know how and where they originate from?
There are pretty good theories now of relativistic jets in black holes. This is a subject that I've done research on for a couple of decades, actually. I work on quasars and black holes and the the jets they produce, which create enormous amounts of electromagnetic radiation across the electromagnetic spectrum, sometimes from radio waves all the way to gamma rays. The theory of how those energy is released near in a black hole started to materialize. In the 1960s, it became clear that supermassive objects, black holes, were the power source in quasars. And in the 1970s and 80s, theorists, in particular Roger Blanford, Martin Rees, produced very elegant theories of what happens near a massive black hole in the center of a galaxy. Basically, the black hole is spinning because it forms from material with angular momentum. It's surrounded by an accretion disk, which is a hot disk of material that feeds into the event horizon and fuels the black hole and also causes its mass to increase slowly over time. And then along the poles of the black hole spin axis, there's the accretion disk is in the equatorial plane, and along the poles there's less material. So there's a natural process whereby plasma, while matter is falling in along the equatorial axis, plasma can be ejected along the poles, and that leads to the phenomena of relativistic jets. The black hole is going to have an entrained magnetic field because, again, it formed from objects that had a less dense magnetic field, and that magnetic field is concentrated in the collapsed object. And so this plasma is threaded by magnetic fields, and that's a perfect situation for acceleration of particles and the synchrotron process of emitting high energy radiation. So through the 70s and 80s, the theory of relativistic jet formation near the event horizon of a black hole, the acceleration of jets of plasma, the acceleration of particles within those jets, because there's magnetic fields involved too, and their production of enormous amounts of radiation, that theory developed and was mature. And in the last 2 decades, we've had supercomputers able to simulate this process and show that the simple theory developed earlier is likely to be valid. And we now compare in detail models of this process to what we actually observe in quasars, and it matches pretty well.
All right, we're well into the session, so I think we'll go ahead and hit up the OsirisRex. Can you talk a little bit about the exciting developments for this mission, and just a little bit of the background and what they're trying to do on this asteroid?
Right. So OsirisRex is, obviously we're very proud of it at the University of Arizona because it's a university-run project. The grant and associated with it is enormous, $800 million. And it's only one of the few times NASA has trusted the entirety of a planetary mission to a university, except for the launch itself, which NASA always does. So the OsirisRex mission has gone to Bennu, a near-Earth asteroid, about 0.5 kilometer in size. And the point of asteroids in this context is that they represent primordial solar system material. So being able to study that material in detail by bringing back a sample would allow you to learn the formation process of the solar system, would allow us to see whether perhaps some of the ingredients for biology already existed in the material that formed primordial objects like these asteroids, and just learn a lot about planet formation and solar system formation from detailed study of a sample. It's very challenging to bring back a sample from close to 1 billion miles away. It takes years. The sample that was captured recently, yesterday, by Bennu, by OsirisRex from Bennu, won't get back to the Earth for about 3 more years. It'll land in the Utah desert with a parachuted canister, and then will be taken to the lab, secure labs. It'll be kept in a vacuum, uncontaminated, until it can be looked at in vacuums in labs. So you don't want to contaminate these samples. The key question, of course, is how much material do you get? Now, since this material is going to be examined atom by atom, molecule by molecule, you don't actually need very much to provide material for dozens of labs to look at their own pieces of it. The minimum bar was set of 60 grams. The OsirisRex mission did a touch and go, TAG as it's been abbreviated, yesterday, and it sent a probe down, which was essentially a reverse vacuum cleaner, or vacuum cleaner that could work in reverse, which was blowing matter off the surface and then sucking it back into a cowling and then into a secure canister and then into the heart of the spacecraft. And it looks like from the video that's been released of what it did, that the material on the surface was loose enough and granular enough that it probably got way more than the minimum amount of 60 grams. So if it got a few hundred grams, that's an incredible success. It also has the ability to go back and get a second sample if they inspect what they found, what they got yesterday, and find that it's insufficient.
So the next question from Mr. Macker is, do we yet know the chemical composition that OsirisRex would have collected in its contact with the asteroid? Are they able to do any analysis on the spacecraft?
Not really. But the spacecraft itself, of course, had a reconnaissance phase where it spent close to a year orbiting Bennu, sort of, warily circuiting its prey before it got a sample. And it used cameras and spectrometers on board to do some diagnostics of the chemical composition of the surface because they wanted to get the most interesting possible sample. For instance, there are some crystalline forms or some paler forms of rock that might be particularly interesting. So they did have some simple spectroscopic analysis to go by, but really the spacecraft has to be kept minimal to keep its cost within bounds and its mass within bounds. So it was never designed to do detailed analysis of the sample itself. The goal is to bring it back, an enormous job to bring it back to the Earth, because then it can be studied in incredible detail for years. Like I said, atom by atom, molecule by molecule, in a way that no spacecraft could ever do. As an aside, that's one of the limitations of the Martian missions. These rovers that we've had on the surface of Mars are not able to do the kind of detailed analysis of rock samples that you could do if you had a Mars rock in a lab on the Earth.
So the next question is, how do scientists know, how are they able to tell if they get the minimum amount of sample on the spacecraft?
Yeah, that's a good question. So the mass of the spacecraft is extremely well known. I mean, it was weighed, it's before launch, and the amount of fuel it's used is known in great detail. So knowing the mass and the mass distribution of the spacecraft, of OsirisRex, it's bringing a little bit of extra mass on board. And so they can spin the satellite and use the moment of inertia or the momentum of the satellite as it's spinning to measure essentially how much extra material was taken on board with the sample. And so that's their way of measuring. It's not extremely accurate, but it gives better than a ballpark estimate of how much was grabbed.
Someone else would like to know, Lisa Hillier would like, Keith Crum would like to know, how does OsirisRex differ from the Japanese asteroid mission?
Yeah, and OsirisRex has had appropriate and suitable publicity, but of course it isn't the first mission to do what it's trying to do. The Japanese had a mission several years ago that sampled an asteroid, and they have a mission that's sort of beaten OsirisRex to the punch actually, and got a sample that will be returned to the Earth at the end of this year in a couple of months. And so they will have that sample several years before the Bennu sample is returned to Earth. So these missions are doing very similar things. Their detailed designs are quite different, but their methods of gathering samples are similar. It's very hard to gather samples from an asteroid because the gravity is so weak, you can't really land on it and tether yourself in a reasonable way. So you have to use a pogo stick or this grab and go with a vacuum cleaner approach that OsirisRex does. You have to have some clever strategies. The reason to do it more than once and for more than one asteroid is these asteroids are going to be different from each other. Each asteroid has a different history. It could have formed in a different part of the solar nebula. The chemistry might be different. The comets, the handful of comets that we've been able to study up close and observe in detail, have proven to be quite different from each other in their composition and their chemical analysis. So you definitely want to have more than one or two to study before you draw a conclusion.
The next question from one of our live viewers is, do you think that mining asteroids will ever become economically feasible?
I think it will. I mean, ever is a long time, and I would guess 20 years is a time frame, at maybe 30, at which asteroids and mining asteroids might become feasible. What it requires is several things. No technologies that are impossible or even extremely difficult. Well, first of all, you have to identify a near-Earth asteroid, that is an asteroid whose orbit brings it fairly near the Earth. And you have to do enough analysis of that asteroid to understand that it's going to have a high return on whatever you might want to get out of it. The ballpark numbers are, if you pick a judiciously selected near-Earth asteroid that's about 0.5 kilometer across in diameter, then it is going to have of order $1 to $2 trillion worth of rare earths at current prices, and almost the same amount, $1 to $2 trillion worth of precious metals at current prices. That's an enormous potential revenue from one near-Earth asteroid. Now, obviously, if you have that much material you're bringing back into a limited market, you could crater the price. So you have to actually be quite careful in terms of how you do the mining so that you don't kill the resource you've just harnessed. So you have to identify the suitable asteroid. Then the technology involved would be to put it in a place where you can mine it at leisure, because if you just rely on its occasional passage near the Earth, that's not a situation where you can mine it. So the strategy would be to send spacecraft out to the asteroid, attach rockets to it. It's not a difficult thing in principle to attach small powered rockets to an asteroid and therefore adjust its trajectory. And what your goal is to take it into an Earth-Moon captured orbit. So not a direct circular orbit of the Earth, that would be too difficult, take too much energy, but a sort of much more elliptical Earth-Moon captured orbit. And at that point, you could potentially set up a mining operation on the asteroid as it goes through this long period orbit, and at the point where it gets closest to the Earth, just start to deliver back the material in stages. That's the general strategy, and there are about 5 or 6 companies that have quite advanced plans for how to do this. So it's a lot of money to set this up and do it. It's going to take years. That's why I said 20 or 30 years. But really, I think it will happen, because the dependence of Earth economy, especially on rare earths for semiconductor industry and other things, and precious metals for other reasons, is not going to change in the next few decades.
Excellent. Thank you very much. The next question is from Meat Roar, who would like to know what kinds of chemical composition could the asteroid contain, and what kinds of chemical compositions do scientists hope to get back?
Well, I mean, scientists, it's sort of similar to the general idea of meteorites. There are metallic meteorites that have a lot of iron and nickel, and there are carbonaceous chondrites that have obviously carbonaceous material and silicon type material. What people might hope for with Bennu or any of these asteroids that we're sampling is that we'd find material that reflects a primordial composition of the solar nebula. So it will really tell us what the proportions of all the chemical elements were in the solar nebula as it formed, because this is the pristine material before it's been altered. Also, we'd want to see what the metallic inclusions are and the crystalline inclusions, because when you form metallic compounds and crystalline compounds, that indicates a thermal history of the asteroid and can show you whether the asteroid has ever been heated and reheated or taken to high temperatures and then cooled in its history, or whether it's always essentially been in the deep freeze of space. So that's another thing. And then the third thing relates to biogenic elements. Obviously, we're very interested in whether some of the basic ingredients for life can form naturally in the solar nebula without being on a surface of a planet, such as the Earth. Obviously, the Earth formed life about 4 billion years ago. But could amino acids or even more complex molecules actually form on small rocky bodies early in the history of the solar system? Because if they could, then obviously as those bodies impact planets or moons, they could carry those biogenic elements to those objects and sort of accelerate, if you like, the formation of life. So people are obviously going to want to look for the most complex carbon, organic molecules that they can find, and in particular the things that are the building blocks of life, which of course fundamentally are the amino acids and other molecules that are used for energy storage in cells.
Excellent. Thank you very much. I think we'll jump topics a little bit. Parzival Fusto, who's on with us live, would like to know, in space, there is a total vacuum, which means we can't hear any sound for sure. But Hubble did make a sonification of two nebulas. So how did that happen?
Right. So sound, generally in astronomy, sound is not a phenomenon because most of space is completely empty. It's a vacuum. So sound does not travel through the vacuum. What we learn about the universe comes from light or electromagnetic radiation. But sound can travel through planetary atmospheres, and it can travel in principle through very diffuse gases, such as a nebula. And so there's a little cottage industry that NASA has done for some decades and other astronomers have done of taking signals that pass through different types of media, including nebulae or plasmas or planetary atmospheres, or the sun itself has been sonification has been done of the sun's oscillations. And basically, if you take any wave-like phenomena that occurs in any kind of medium, you can sonify it. You can convert it or up convert it or down converting it, depending on the frequency, into audible sounds. And those audible sounds would, of course, have to be in a frequency range from a few dozen hertz to maybe 10,000 hertz is the highest frequency people can hear. And so this is done naturally. It's not realistic, of course, because again, these sounds are not really audible in these situations, but it's a very interesting way to give people a sense of vibration and oscillation phenomena in different and exotic astronomical settings.
All right, the next question is from Astronomy Club, who would like to know, if the universe expanded in all directions after the Big Bang, then why is it called flat and not spherical?
Right, it's a good question. The expansion doesn't really talk about the underlying or the nature of the expansion into something. In other words, in the Big Bang theory, there doesn't have to be reference to an external medium. So it's not even appropriate to consider the expansion taking place into some surrounding medium because it's the entire universe that's expanding. Now, in principle, because the universe was very small and very high density, the gravity of the universe should have made space highly curved at the beginning. It's only because the universe is expanded by such a large factor and is now very old and enormous that we observe space to be nearly flat. And so that's a direct observation that space is flat, even though space-time could be curved according to general relativity. That's not what we observe. We observe flat space-time. And then the limit, or what's beyond the limit, is just a matter of operational definition that we can only see distances as far as light could have traveled in 13.8 billion years, the history of the universe. So we really can't comment on the nature of space-time beyond our horizon, which is the limit we can see according to that time limit of the age of the universe.
The next question is a little bit philosophical, and I know you can handle those and enjoy them. One of our live viewers would like to know, do physicists, or astronomers in this case, believe in good and evil? When we canvass the universe, will we find extraterrestrial good and extraterrestrial evil?
That's an interesting question. I'm part of the loose community of astrobiologists and people who do SETI, search for extraterrestrial intelligence. And so I do have conversations with colleagues about this, and I've obviously read about it and written about it at some level. Yes, the sort of ethical nature of the universe is an interesting question. As soon as you acknowledge that life in the universe is likely to be fairly abundant because the ingredients are abundant, and there's no reason if you have liquid water, an energy source, and carbon-based material, you shouldn't get biology eventually. It's it's on the table that if you have intelligent or sentient life, does it have a basis in good and evil, or is there an ethical framework that applies to life beyond the Earth? It's hugely speculative because we don't even know about any form of life beyond the Earth, let alone advanced or intelligent life or sentient life. But it doesn't stop people from having conversations about it. I think there's even entire books have been written about it, ethics of extraterrestrial life. And I think the obvious danger is we just project our own values, our own experience, our own ideas of good and bad or good and evil into a larger framework where we don't really know what the rules are. We don't even know what the rules are on our own planet. If we believe that octopuses are intelligent, which they seem to be, or orcas, and sentient, which they also appear to be, then do they have an ethical framework? Do they understand good and evil? If we can't even answer that question for other species we share the planet with, then it's obviously exceptionally hard, essentially impossible, to answer that question for species beyond the planet. So while we might think that if biology is present elsewhere in the universe, something like Darwin's natural selection would apply to life as it evolves elsewhere, that's a plausible hypothesis. I don't think it's really a plausible hypothesis to project that ethical frameworks or senses of good and evil apply elsewhere in the universe. We just don't have enough information to say that.
The next question is from Sumik 777777. The Wide Field Infrared Survey Telescope, WFIRST, and the Nancy Grace telescope will be searching for exoplanets using microlensing. Can you please explain this method and talk about its limitations?
Right. So the two facilities mentioned are sort of the premier facilities for doing big survey work in the next 5 or 10 years. And they are the Nancy Grace Roman telescope, recently renamed. It was the Large Scale Synoptic Survey Telescope, LSST, before that, and WFIRST, which is a NASA mission, which has had multiple iterations and has had a lot of delays, but appears that it might launch in 2025 or 2026, and it's a survey telescope in space. So these survey telescopes are indeed good for microlensing surveys. The point about microlensing is it's a needle in a haystack experiment. If you're looking for a planet by microlensing, an exoplanet by microlensing, you're looking for the very rare and occasional circumstances where the exoplanet passes directly in front of a more distant star, and so lenses the light from that star by the effect of general relativity. It's called microlensing because the deflection, the angular deflection of that lensing event is far smaller than you can resolve with a telescope. It's micro arc seconds essentially, as opposed to arc seconds or milliarc seconds that you can see with a telescope. So you don't actually see multiple image formation. All you see is the effect of the magnification. So you get a transient magnification of the background star caused by the passage of an exoplanet in front of it. So the strength and the limitation of microlensing surveys are, the strength is that it's very sensitive technique, and it's quite a particular signature. When you see a star suddenly and symmetrically rise in brightness and then fall, and then it never repeats, that's not a variable star, that's a particular event that occurred. So microlensing gives a very particular signal, and you can measure the mass of that star, of the lensing object by that. And the sensitivity is good enough to see things smaller than the Earth, maybe as small as Mars, and maybe even smaller than that. So it's a very sensitive technique. The downside is that it's a one-time event. Because that exoplanet attached to a star is passing in front of a more distant star, that passage won't recur. So it's a single event that you measure, and then it never repeats. And because the fraction of space involved in an exoplanet passing in front of a star is very small, you typically have to look at about 1 million stars for, say, a particular night to have a chance of seeing one of them involved in a microlensing event, hence the needle in a haystack experiment. So you need these big survey telescopes, which are looking at tens of millions of stars at once, to have chances of seeing microlensing. So with existing telescopes and surveys, only a few dozen microlensing exoplanets have been found, a very small percentage of the total. But with these big telescopes in the future, that could change. And so we may have hundreds or even thousands of exoplanets found by the microlensing method. And like I said, it's sensitive to very low mass exoplanets, which is quite exciting.
The next question returns us to the topic of asteroids. Lisa Hillier has noted that the sample return from OsirisRex is due to be returned and land in the Utah desert where she lives. Is there any way to find organizations or universities in a way to get involved with working or, somehow get involved with those kinds of things?
I mean, they're in principle possibly, because the samples are going to be widely deployed. I mean, whatever sample is finally collected will be taken from the Utah desert where it lands, and it will be of course, in a sealed canister so that it's not contaminated. It won't be contaminated in space, which is a vacuum, but when it goes through the Earth's atmosphere and lands on the Earth, there's a potential for contamination. So it's a very carefully sealed interior canister. And then it will be taken to NASA's secure facility. It's at Johnson Space Center. It's where the lunar samples were taken and are still housed. It's a level 4 biocontainment facility, so extremely secure in case there are microbes or germs. We don't expect that, but it means it's extremely secure from contamination and secure to keep the samples safe. And then it will be divided up in dozens of different microsamples and sent to labs around the country. I would suggest going to the OsirisRex main website, either the NASA website or the Lunar and Planetary Lab website here in Arizona, because they will list who their collaborators were, and I'm sure there's a document somewhere on those sites that says which research groups are expected to get samples, and that may be a list that's still expanding. Now, they're not going to give material out to individuals or amateur astronomy groups or other small groups of people. I think they will have to go to groups at the level of research institutes or major universities, and because it's high demand, of course. But I think you could probably find that information online.
Excellent. Thank you much. The next question is from an email. During the initial stage of star formation, what is it that causes the interstellar cloud of molecular dust and gas to contract?
It's essentially a gravitational instability. There are some nebulae or clouds of gas and dust that never collapse. They aggregate. Maybe gravity is holding them loosely together. They have some turbulent motions or circulation motions. Maybe eventually they dissipate. Sometimes the differential rotation of the Milky Way itself pulls apart a very large gas cloud, and so it never collapses. So it's not a given that a big nebular dust and gas cloud will collapse. However, if it does get to a certain density, there's a minimum threshold density, then the level of internal gravity will cause it to start to collapse. And the nature of gravitational collapse of these clouds is called inside out, where the interior of the cloud collapses first, and as it collapses, of course, the density increases, the gravity gets stronger, so it's a kind of runaway process, and it's essentially gravitational freefall, and that's how stars form in these dense clouds. Meanwhile, the exterior regions of the clouds are maybe not very much affected at all. So only a fraction of the material in these large diffuse clouds actually ends up collapsing into the form of stars. And like I said, some of these clouds never collapse at all. So all sorts of things happen. However, we do see in general that the size of clouds that form stars are sufficient to form not just one star like the sun, but to form dozens or even hundreds of stars. The Orion Nebula is a perfect example of that.
The next question is from Alpha Astronomia. What's your opinion about the possibility of using quantum entanglement as an instantaneous communication method, or will there always be the limitation of the speed of light?
Well, that's a good question. And we just don't know enough about these experiments to say what the eventual utility might be for communication. It is true that quantum entanglement experiments that have been done in the lab, and some entanglement has been demonstrated on actually large distances of thousands of kilometers between distant locations in Europe, I know in particular. It does indicate that information is instantaneously held at two remote locations. That's very interesting because that essentially says that physics is non-local, and that is, essentially rebutting what was one of the premises of classical physics, that information can only travel with light speed and no faster. Now, how do you turn that into a instantaneous communication mechanism? Again, nobody really knows the answer, because to set up these experiments And to control them and to monitor the conditions of these experiments, you have to use more conventional means, which involves sending light signals. And so there's limited by light speed. It's only the entangled states themselves that are apparently held simultaneously at remote locations. So I think the simple answer is that no one's figured out a way to turn this phenomenon into a practical communication technology.
The next question is from one of our live participants, Mayaz211. How can energy be extracted from a black hole?
Well, energy can be extracted in a couple of ways in principle. We see energy being extracted. Now, it's not that the energy that comes out of massive black holes in centers of galaxies that turns them into quasars or active galaxies, that is technically not energy being extracted from the black hole itself. That is gravitational potential energy of matter falling into the event horizon or towards the event horizon, using that gravitational potential energy to convert into kinetic energy and then heat or radiation energy that then leaves the vicinity of the black hole. So that's not the black hole's energy itself. It's using it as a gravitational engine, however, and that's how astronomers refer to it. The more direct way to extract energy from the black hole, there's two ways. There's the natural way, which is black holes are supposed to have a temperature, according to Stephen Hawking, and Hawking radiation is energy leaving the black hole, causing it to slowly evaporate. So if you could find a way of harnessing the Hawking radiation from the black hole, you could extract that thermal energy. And people have written papers about constructing what are called Dyson spheres. Dyson sphere is the idea of constructing a sphere close to the sun to trap all of its energy rather than the 1 part in a billion that we get on the Earth at a distance of 150 million kilometers. You could put a Dyson sphere around a black hole and trap the Hawking radiation and then do something with it. It's a very small amount of energy, though, not very useful. A second way, however, to extract energy from the black hole is to take advantage of the fact that the black holes are rotating. Every black hole forms from an object with angular momentum, and so it's spinning quite fast because it's collapsed so much. And there are methods, and Freeman Dyson has talked about this, and also Roger Penrose, who won the Nobel Prize very recently, has talked about this, of a civilization or some clever intelligent entities sending projectiles or probes very close to the black hole, but not to the event horizon, actually to the ergosphere, which is twice the distance of the event horizon. And if you send it in and then out again, so it's not trapped and retained, you can use a probe or projectile to extract a tiny amount of angular momentum from the black hole. So the object comes out with more energy than it was sent in with. And so that becomes a way of extracting rotational energy from the black hole and gradually spinning it down. So those are hypothetical ways you could get energy out of a black hole.
Excellent. Thank you very much. The next question is from one of our live viewers, Mr. Macker, who would like to know basically how are we able to look at times back in the universe. So the question specifically is, if we are using light to observe the known age of the universe, and given that light from stars did not exist for some time after the Big Bang, then how are we going to measure the period from the initial pinpoint to the first light emitted from the first stars?
Right, that's a good question. So in the chronology of the universe, there's a period of time when the universe was small, before gravity had a chance to make stars and galaxies. It's called the Dark Ages. And so until the first light in the universe, whether it's stars forming before galaxies or the other way around, the universe is dark. And so a natural question is, how do you know how to measure time back before the first light? And the answer is we don't. There's no direct way to measure time. The measurement of time in the Big Bang model is based on a model of the expansion. So we basically do have to know what the material and energy contents of the universe are to make a model of its expansion. So we measure its present expansion. We can look in the nearby universe to measure its current expansion rate. And then with its current expansion rate allied to a measurement of the total amount of mass, mostly dark matter, and energy, mostly dark energy, in the universe, you can make a cosmological model. And it's that model that tells you what times were in the first part of the chronology. There's no direct measurement of stars or galaxies that will help you. So it's really based on a model.
Some of our Twitch viewers are new and haven't heard some of the answers to basic questions. Duck, who's on with us live, would like to know if you can explain the Higgs boson and why it is so important.
The Higgs boson is the crowning achievement of what's called the standard model of particle physics. The standard model of particle physics is a schema that says we have heavy particles, like the 6 flavors of quarks that form normal material of neutrons and protons, and we have light particles, or leptons, which include things like electrons, which are in every atom, and neutrinos, which are also abundant in the universe. So the standard model of particle physics has these sets of particles, heavy and light, and 4 forces of nature. But the standard model doesn't really tell us where mass comes from, or why masses are different for the different types of quark, for example, or why the electron is 2,000 times less massive than a proton or a neutron, for example. The Higgs mechanism and the Higgs boson don't actually describe why particles have the particular masses they do, but it provides a mechanism for why particles have mass. So we imagine the Higgs particle really to be a Higgs field, or something suffusing space. And essentially, if you want to make an analogy, imagine particles moving through a viscous field or fluid, and the resistance in that fluid is a sense of their mass. Particles with more viscosity or inertia or resistance have heavier mass, and particles with less or have lighter mass. So the Higgs field accounts for high and low mass, and essentially gives a mechanism for mass by this means. And it was a prediction for the 1960s. The particle was detected, the field was detected in 2013, 2011, 2012 to 2013, and a Nobel Prize given a few years later. So it's a very important piece of our standard model of particle physics.
Excuse me, Jagux would like to know if you could explain the second plane of the solar system other than the ecliptic.
Right. Well, the solar system is, I mean, it has a primary and fundamental plane, which is the ecliptic, because that's the, that's the orbital path. The ecliptic formally is the path of the sun through the sky as seen from the Earth. So it's basically, the ecliptic is the Earth-Sun plane of the Earth's orbit. Now, the solar system, of course, has other planes, because not all the planets are in the same plane as the Earth-Sun orbit. In fact, none of them are. They're all slightly displaced. And so there are different angles or tilts of the orbits of different planets around the sun by several degrees. And so it's not really just one plane of the Earth-Sun. It's a set of planes closely aligned of all the planets. And these are, of course, are fundamentally aligned with this angular momentum axis, or the spin axis of the sun, which dominates the mass of the solar system.
Excellent. Thank you very much. The next question is from Jeffrey 4210. Are accretion disks for black holes unique? Let's see. Are accretion disks for black holes unique to quasars? I guess. Are accretion disks unique to black holes, or do other phenomena in the universe have those?
That's a good question. Black holes definitely have accretion disks. Now, an isolated black hole won't have an accretion disk. I mean, it has no way to get material if it's isolated in space. Most of the stellar mass black holes we know about are in binary systems, and so they're siphoning material off their companion star into an accretion disk. Most of the massive black holes that we know of at the center of the galaxy, of all galaxies, also have material available, and that will swirl into an accretion disk around the central black hole and make them episodically active, like an active galaxy. Yes, there are other objects that can have accretion disks. Other kind of compact stars can have accretion disks. So neutron stars and pulsars could have accretion disks. And so, any very compact form of star could in principle have an accretion disk, especially if it's in a binary system.
Excellent. Thank you very much. The next question is from one of our live viewers who would like to know, Parzival Fusto would like to know, there is news that Betelgeuse is on the verge of going supernova. He says earlier than estimated calculations. Is there any reason that we either lost the calculations or maybe we didn't understand how stars go supernova completely?
I think the situation with Betelgeuse is muddied because we never are going to have good enough information about Betelgeuse and the stage it's at in its evolution. These variability measurements are diagnostic of things happening in the outer atmosphere, remember, of Betelgeuse, or in the surrounding region of the outer atmosphere. They're not diagnostics of the fusion zone itself. So we have very indirect measurements of what's going on in the fusion core of Betelgeuse. And without that, we're never going to be really certain what stage it's at in its evolution, what nuclear fuel it's using, how much of that fuel it's used, and therefore how much is left and how long before it goes supernova. So the model that says that's the fate of the star is fairly reliable, and we've simulated and modeled it in detail with supercomputers. But our observational information is just too crude to assign a time to that event in the case of Betelgeuse. We do know it's going to happen, and the things we're measuring about it suggest instabilities that do occur very near the end of a star's life, but it's very crude information, not enough to assign a predicted expiry time or detonation time to that star.
Student McLeod would like to know, why should we accept that blind chance led to Earth's initial living cells when the best efforts of brilliant biochemists with advanced labs and modern technology cannot generate living cells?
Well, that's a good question. So the premise of modern astrobiologists, astronomers, and biologists is that no special conditions were required for life on Earth to evolve. No divine intervention or intelligent design was involved. It's all natural processes. And so it's a legitimate question is, what are those natural processes? And can we understand them in detail and simulate them in the lab? Now, at some level, it should not be surprising that it is difficult in a lab to reproduce what happened in very alien and extreme conditions on the Earth and what may have taken hundreds of thousands or millions of years to occur. To be able to do that in a lab is a tall order. And it's not entirely true that lab physics or lab chemistry and biology have failed to tell us how that process might have happened. Actually, some labs, Jack Szostak is a good example. He won the Nobel Prize for work on telomeres a few decades ago, and since then has devoted the entirety of his lab research to simulating the processes that occurred for life to start. So what has been demonstrated is that simple molecules present on the early Earth could combine to form amino acids and the various energy containing and lipid forms of molecules that are required for life. The first primitive protocells, smaller than present-day cells, have been formed naturally, the containers at least, in lab conditions. And also lab conditions have been able to take particle templates or clay-like surfaces as templating surfaces within these protocells to build significant fractions of RNA, that is, fragments of RNA that include hundreds or even 1,000 atoms. That's quite significant. That's not close to a replicating molecule. It's obviously not a full cell. But in terms of the steps along the way, connecting the dots, it's actually quite a significant achievement. These are just very difficult experiments, and there's only a handful of labs doing this around the world, so it's kind of slow progress. But there's still nothing that's been learned in the lab that suggests that magical or divine intervention is required for it to happen. It's just a lot of time required for it to happen.
The next question is from Smayana, who would like to know, is dark energy the same thing as vacuum energy?
Possibly. Some physicists would like to make that connection because dark energy pervades the universe and is causing the accelerating expansion of space-time. And vacuum energy is a phenomenon that's been known in physics for almost a century. The pure vacuum, whatever pure vacuum you can create, is not completely inert, but contains this very small amount of quantum energy, zero-point energy as it's called. And we can see manifestations of that vacuum energy. It can create a pressure in certain lab experiments. It can lead to the formation of particle-antiparticle pairs that appear and disappear. So there is vacuum energy in physics, and there's dark energy in the universe. But when you try and connect them, you fail miserably. Standard physics is incapable of explaining why the dark energy we see in the universe is as weak as it is, ironically. That when you do simple calculations in quantum theory for the vacuum energy and then apply it to the universe as a whole, the strength of the vacuum energy is just far too strong by many, many orders of magnitude. And so those simple calculations fail. And so while the two may be related, they can only be related in some theory that we don't have access to at the moment because the simple calculations don't work.
So the next question is from an email. Pridrag Ivosev would like to know, what are the top unanswered questions in astrobiology today, and what are some of the main focuses of research?
Yeah, astrobiology is a very dynamic field. It's a small fraction, maybe only 10% of all astronomers that are working in that field, but it's growing because of the boom in exoplanets. So I'd say well, obviously the fundamental question of astrobiology is, does life exist beyond Earth? Because we still don't know the answer to that question. So I think all other questions are secondary to that one. Given that that's the primary question, the questions that can be addressed by observations are how many Earth-like and habitable planets are there, either near the sun and the moon and the Earth, or all across the Milky Way projected to a number. So what's the habitable real estate of the galaxy? That's a question that astrobiology is going to solve. Another question that astrobiology is dealing with is how many and what type of habitable locations are beyond the traditional habitable zone, that is the Earth around the sun, able to have liquid water on the surface. We know that there are places far from stars where water can be kept liquid by pressure, by tidal heating, by geological heating. And so if you can have all the ingredients for life far from a star, then the number of and type of habitable locations in the universe is now an open question too, and we'd like to know the answer to that. Assuming we can detect biology, another very difficult question to answer is, how strange could life be? How different from terrestrial biology could biology be elsewhere and still have us able to recognize it or see what it is? That's a very difficult but also very fundamental question. And then the final question, which of course presumes that there is life elsewhere in the universe, is in what fraction of the cases where biology develops at all or for any reason or anywhere does that life eventually become sentient, intelligent, or develop technology? That means, are we alone in the universe?
All right, this is going to be the last question for today. We've gone just about an hour. Thank you everyone for joining us. But if you could wrap up by talking a little bit about Ravi would like to know, we hear about the results of observing campaigns, but getting telescope time on big telescopes can't be easy. So how do observational astronomers get access to scarce ground-based telescope resources these days?
Yeah, that's a good question. It's been a renaissance of big telescope building in the last few decades. So there are large telescopes around. There's over a dozen telescopes of 6 to 8 meters or larger. So it's a good time to be an observer using large telescopes, but there's also a lot of astronomers. So I would say in round numbers, and I spent a lot of my professional life trying to use telescopes, getting accepted for time and turned down for time. Basically, for the typical large telescopes, either in space or on the ground, the oversubscription, which is to say that the ratio of number of people asking for time or the amount of time they're asking for relative to the amount of time available, is a factor of 4 to 6. That's a pretty high factor for the large telescopes. For small telescopes, not so much. In fact, some small telescopes' time is going begging, basically. There are not enough people applying for the time. But for the big telescopes, only about a quarter of the proposals, or maybe a sixth of the proposals, actually can get time. And that's a pretty big down select, and that means that a lot of people have really good ideas that don't get time. Hubble Space Telescope, it's a similar factor, maybe as high as 8 or 10 to 1 in some cycles. So getting telescope time is hard. Sometimes if the time is awarded every 6 months or a year, you have to wait a whole year. Sometimes you could have 2 dry years in a row and wait 3 years, so you have to be very patient. Also, it's worth pointing out in space, this doesn't apply because the weather doesn't affect you in space. But for ground-based telescopes, when you get telescope time, you're subject to the second lottery, which is the weather. So if you happen to get through this competition and get your time and it's cloudy the whole time or most of the time, too bad. You have to try again. Now, in the process of the competition, that's not held against you. So if you get awarded time and then that time is cloudy, when you come back again, you tend to have a better chance of getting the time. They'll definitely try and give you the time. Also, more and more large telescopes now use Q observing. So rather than scheduling very particular nights and having a detailed schedule where observer X gets nights 1, 2, and 3, and observer Y gets nights 4, 5, and 6 on through the calendar, now they have a Q scheduling where if you get time, you're assigned a priority, essentially the likelihood that your data will be taken, and that data is taken whenever possible given the observing conditions. And that increases the probability, if you're highly prioritized, that you'll get your data regardless of the weather. So that's a favorable thing, and most astronomers like Q observing for that reason. It's also more efficient for the observatory. It means more science gets done because the weather isn't a wild card for everyone. So that's how modern telescopes work, and it's hard. The other thing that happens in the margins is that most observatories tend to give precedence to people at critical stages of their career, and typically that means graduate students. So if you're a research student, graduate student studying for a PhD, and your project, your observing time is for your PhD, which you have to get in a certain period of time, then most observatories will prioritize, all other things being equal, assuming it's good science, will prioritize that time. And that's to ensure that graduate students who only have a finite time for their thesis get their data. A professor, a senior professor who's been doing research for a decade or 2 decades, they can wait a year with no problem. So that's a sort of thumbnail sketch, but it's a very competitive process, and astronomers are often disappointed. They often don't get the time they want, the time they need, or the time they request. So thanks for that. That was a good question. I hadn't had that one before in all our sessions, and we got a lot of range today again, and hopefully the new model we're using will be good for everyone, and we'll be with you again next week. Thanks very much to Matthew and Vicky for facilitating, and Alexander, as always, behind the scenes.
Excellent. Thank you very much. And to those of you who are on with us, make sure that you follow the channel. And if you can subscribe, that always helps us out. And just so you know that all of these sessions, these live sessions, will be archived. We can upload them 24 hours from now on YouTube. So if you come back to this channel, it will be available for a while, but it will permanently be available on our regular YouTube channel. So thanks all for coming, and we will see you next week.